Okay, hello. We're going to do these three related rates problems. The first one, number 25, says, I wrote the whole problem here on the board, a swimming pool is 12 meters long, 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. Water is being pumped into the pool at a rate of 1/4 of a cubic meter per minute, and there is, I added this in, this is my sort of parenthetical, at the moment there is 1 meter of water in the deep end. What percent of the pool is filled, and at what rate is the water level rising? Okay, well, it's pretty good that they added a picture here, because I'm not sure you would 100% be able to reconstruct this this figure from just this description. But okay, what kind of pool is this? It's 12 meters long, 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. Well, okay, yeah, I don't know if that's the greatest explanation ever, but anyway, there is a picture, and the picture looks something like this. A cross-section of the pool is kind of like so. So that's 3, and that's 1, and it kind of comes in like that. So that's the kind of shallow end, and that's the deep end. And then, you know, it's a pool, right? So it's coming out like, let's see, how do I even draw this? It's kind of been a while since I've tried to do this. Jump, and then maybe something like this. So, wow, and then something like that. So, boom, and then boom, and then boom. Okay. Never mind the dashes versus, okay, so what is this shape? This shape is in fact a trapezoidal prism. It's a prism whose base is a trapezoid, and okay, that's 3, that's 1. What are the dimensions of the pool? Well, it's 12 long and 6 wide. I don't think that those words are unambiguous enough that would have been clear to me, but this is 6, and in fact this is 12. Okay, so in other words, what are we talking about here? What we're talking about is a pool whose shape is as follows. There's a trapezoid here, and this trapezoid has bases. The bases of the trapezoid are the parallel sides, of course, which are 1 and 3. And one of the legs of the trapezoid is 12, and the other one is, I don't think I even care right now. Okay, and the height of the prism, so to speak, is 6. So that's the shape of the pool. And all right, so the pool is like, so okay, so let's go back to the problem. Let's go back to the text. The swimming pool is 12 meters long, got it. 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. Yeah, I guess this is kind of like how pools are, now that I think about it. Water is being pumped into the pool. Okay, so that's the other thing that's happening, is we're pumping in water. So there's some kind of action now, finally, and water is coming into this pool. And yeah, we know the rate at which the water is being pumped in. And there is, at the moment, 1 meter of water at the deep end. Okay, so you have to kind of imagine, so this is the shallow end is 1, the deep end is 3. So 1 meter deep is like that much, right? And okay, they want to ask about 1 meter, but in fact, since the water level is changing, I want to do something sort of a little bit more general than 1 meter. I'm going to draw in the water kind of looking like this, and I think this will make the picture a little bit more clear. I see now that my diagram is not so good, but anyway, whatever. So the crucial sort of observation here is that the pool may be in the shape of a trapezoidal prism, but the amount of water that we're filling the pool with is not so much. So in other words, our water level is never going to reach the shallow end. We are not, in this problem, considering what happens when the water level is too high, as in 2 meters high. When the water level is 2 meters high, as measured from the bottom of the deep end, then we're going to finally start to get some water in the shallow end. At the moment, the shallow end is completely empty of water, and in fact, since the problem is asking what happens around the time that there's 1 meter of water in the deep end, then the fact that this shape is a trapezoidal prism is actually kind of irrelevant to us. It might as well be a trapezoidal, it might as well be a triangular prism. Okay, more on that in a minute. Blah, 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 blah. I was going to say something else, maybe not. Alright, let's do the problem. What's happening? Water is being pumped into this pool. The pool is of a particular shape, and the water is being pumped in at a constant rate. What is the water doing? It's filling up the pool. And as it fills up the pool, the water level keeps rising, and okay, so that's that. So okay, read and understand the problem. Draw a picture. I think we've done that. Pick variables for the quantities which are changing. Well, what are the quantities which are changing in this problem? I claim that one thing that's changing is the volume of the water. Another thing that's changing in this problem is the height of the water at any given moment. And maybe that's it. Maybe those are the only ones. I'll leave a blank for possibly more. So read and understand the problem, draw a picture, pick variables for the quantities which are changing, add those variables to your picture. So I'm gonna create a new variable called h, where h represents the what I'm gonna call the height of the water, but of course that's measured from the bottom of the deep end. So it's this quantity right here. It's this h right here. Okay, great. Great. Well, what's next? What next? Add those variables to your picture. Pick variables with quantities, add those variables to your picture. Restate the information given in the problem in terms of those variables. Okay, so what are we being actually told? We're being told that water is being pumped into the pool at a rate of 1/4 of a cubic meter per minute. So I know the rate at which the volume is changing. dV dt is 1/4 of a cubic meter per minute. This is what I know. And what I want to solve in this problem ultimately is at what rate is the water level rising. So I want to know what is dH dt. And okay, I hope you feel that dH dt is not going to be constant, because when the very initial burst of water gets dropped into this pool, at first the height is going to increase very rapidly, but then it seems, this is what my intuition is telling me, and I think the math will prove this, that as the water level gets higher and higher, it's going to take more and more volume of water to achieve an increase in height. So I think that dH dt is going to be the rate at which the height is changing is going to be small at first, big at first and then small later. Okay, let's see. We're going to do calculus and find it out. And we might as well say now that while finding the formula for dH dt is maybe the most interesting part of this problem, and we actually have to do that, the answer to the problem doesn't ask for dH dt in general. It asks for dH dt at the particular moment at which there is 1 meter of water in the pool. That's a little bit vague, I think, but if you read it several times, you'll see that that's what they're asking. So the answer to this problem, which is going to be a number, is going to be what is dH dt when h is 1. Okay, now we are going to kind of start the problem finally, and notice that they threw us like a little tiny challenge, not challenge, they threw us like a small intro kind of problem to help us through this. In other words, part A of this problem is actually not calculus at all. Part A of this problem is just a simple basic geometry problem, but and the question is, what percent of the pool is filled? Okay, well, to find the percent of the pool that is filled is just forcing us to, before we get too bogged down in the calculus, it's forcing us to make sure that we understand the actual geometry of this pool. And so, okay, so let's answer this part A right now. And as I've already mentioned, the volume, the pool, the shape of the pool is a trapezoidal prism, but the shape of the water that is in the pool is a triangular prism. Okay, so let's just calculate right now the volume of the pool. So what is the volume of the pool? Actually, let's do it the other way around. Let's calculate the volume of the water, and then we'll calculate the volume of the pool. And well, okay, that will just be it, right? That's the thing we're trying to find. So what is the volume of the water? Well, the volume of the water is just a kind of a triangular prism, right? So I need to find the area of this little blue triangle of water, and then I just multiply it by 6 because the triangular prism of water is 6 meters high. All right, so how do I find that? Well, it's only now that I'm finally sort of realizing that yes, the deep end has depth 3. But more relevant to me is that there's this kind of imaginary line here that I get from dropping a perpendicular down from the kind of shallow end point to the deep end point. And this distance here is 2. In other words, well, I think that's pretty clear from this picture, right? The 2 is left over because the shallow end is 1, the whole deep end is 3, so this is 2. And yeah, then this is kind of 12. And so what we have here is a triangle. And the dimensions of this triangle are that this is 2 and that this is 12. Right, and so you can't make any progress on this problem until you realize that my triangle of water is partially filled in from this triangular prism of pool. And therefore, that's my triangular prism of water is going to be, well, it's a little bit of an exaggeration to say that it's similar to the pool, but this triangle is certainly similar. Okay, let's just kind of get to it finally. Basically, what I'm now realizing is that if I want to find the area of this triangle, I need to know 2 things. I need to just know, the base and the height. Well, the base of this triangle, you might say, is just h, what I've previously called the height of the water. But what is this other dimension? They don't seem to give that to us in the problem. Well, they don't need to give that to us in the problem because based on the geometry of the pool, this has to be 6h. Why is this 6h? Because this triangle of water is similar to the triangle of the pool. And since that's 12 and that's 2, they're in the ratio of 12 to 2 or 6 to 1. So if that's h, then that has to be 6h. So you could invent another variable for that, I suppose, if you want. I don't even know what I would call it. I would call it sort of the the width of the water or something like that. The length of the water. But anyway, that's 6h. What's the point of all this? The point of all this is that if I want to find the volume of the water, I should find the area of that triangle, which is going to be 1/2 times h times 6h times the height of that prism. And the height of that prism is the width of the pool, so that's times another 6. Okay, and now if I want to find the volume of the pool, well, now I just need to find the area of this purple trapezoid, the large purple trapezoid, and multiply again by 6. What is the area of this purple trapezoid? Well, the area of any trapezoid is the average of the bases times the height. So that's going to be the average of the bases, so 1 plus 3 over 2 times the height of the trapezoid, which is 12, times the height. Sorry, this shouldn't be 6. Everything I've just said is true, but I'm realizing now that I'm doing actually too much because I want to know what percent of the pool is filled when h is 1. So let me just change it to h being 1 temporarily. Well, if h is 1, then this 6h is 6. So therefore, the area of that triangle is going to be 1/2, like times 1 times 6 times 6. There you go. Sorry about that. Because of course the answer to this is going to be a number. Okay, and then the average of the bases times the height. So this is 24, and then we are going to multiply that again by 6 because it's the height of the trapezoidal prism. Okay, so the 6's cancel, more 6's cancel, and I think we just end up with this just being 1/8. Okay, and so the answer is that 12.5% percent of the pool is currently full when the depth of the water is 1. In other words, when H is 1, and therefore this 6H quantity is 6, I've calculated the value. Okay, let's keep going. All right, I'm glad we did that problem because I'm now feeling more confident about this whole situation. All right, so read and understand the problem, draw a picture, pick variables for the quantities which are changing, add those variables to your picture, restate the information given in the problem and the information requested in terms of those new variables. Finally, we are going to find a formula, find a relationship between the variables. What is the relationship between the variables? Well, we've done all the hard work already, right? What is the volume of the water? The volume of the water is going to be the volume of this triangular prism. So that's 1/2 base, which is h, times the height of that triangle, which is 6h, times the height of the prism, which is 6. And therefore, this was seemingly kind of hard, but then it just got sort of easy, right? What is the relationship between V and H? It's just 18h squared. So give me the height of the water in the pool, and I can tell you now what the volume is. Give me the volume, and I can tell you what the height is. And this formula will remain valid as long as the water level in the pool is less than 2. As long as the water level in the pool is less than 2, the shape of the water will be a triangular prism. And so this is the correct formula. Okay, anyway, now that we've done that, now we can rephrase the information given in the problem. Now we can just take the derivative of both sides. So I take the derivative of both sides, I get dv dt equals, what is the derivative of 18h squared with respect to time? It's going to be 36h back inside for the derivative of h, which is dh dt. So I'm doing the chain rule here. The derivative of something squared is 2 something back inside for the derivative of that something. Okay, good. Now what? Well, I guess now I'm kind of done, right? What is dh dt? Answer, dh dt is dv dt over 36h. And this, to me, is kind of like the best formula. It's the formula which kind of explains what dh dt is. It's oh, by the way, we can now reflect back on our intuition from earlier, and we can see that indeed, when h is very small, dh dt is quite big. But as h gets bigger, dh dt gets smaller. Okay, so this is the sort of formula in general for dh dt for this pool, but now we add in the fact that dv dt is a certain kind of constant, so therefore dh dt is, setting dv dt equal to 1/4 gives me 1/4 over 36h, which is 1 over 108h. And now finally I can answer my numerical question, which is, what is dh dt at the moment when h is 1? And when h is 1, this is 1 over 108, and the units are meters per minute. Okay, woo! Good, back for 2 more in a second. Okay, number 29. This one's a little bit harder, I think. A winch at the top of a 12-meter building pulls a pipe of the same length to a vertical position, as shown in the figure. Okay, let's figure this out. What is a winch? Okay, I may have never used a winch in my entire life, but okay, let's just sort of tell the story or something like that. You have some kind of building, all right, and buildings are, generally made perpendicular to the ground. And here you are up at the top of this building. And let's say you have some kind of a pipe. And this pipe is going to, carry water or something like that. And you need this pipe to run vertically along the building. Well, how are you going to get that pipe up to the building? Okay, if the building's only like 10 feet tall or something like that, maybe you're just strong enough to, push the pipe up to the top of the building. But if the building is very tall, and this building is 12 meters tall, so that's like 36 feet. Now this pipe we're talking about is like very, very tall. And let's see, if that's 12, that looks kind of about right. And so like now your just puny little arms or whatever reaching up, trying to push this pipe. Okay, perhaps if this pipe is weighs very little, and perhaps if you're very, very strong, you can just keep pushing and pushing and pushing and walking your way towards the building, just pushing really hard and kind of just swing that thing up against the building vertically. But that's maybe not a good way to do it. And if the material is delicate or perhaps very, very heavy, then this is sort of a bad way to get your pipe up. So what's a good way to get your pipe up to the top of the building? Answer, to pull it up. So what you're going to do, instead of what I just was indicating, instead the sort of professional thing to do, this building is 12 meters high, is to climb up to the roof of the building, throw a rope down from the roof of the building, attach the rope to the end of the pipe, attach the bottom of the pipe to the point here at the base of the building, and then pull the rope up. And so that is what is going on here. So what is a winch? A winch is a object for just pulling in a rope. It's probably a mechanical one. Would probably be some kind of thing where you had a rope on a spin, and you just were kind of cranking some sort of shaft, and you were just pulling in the rope. And as you're pulling in the rope, you're making the rope shorter and shorter. And as you're making the rope shorter and shorter, you're pulling the end point of this pipe. This is the pipe. Maybe I should draw it looking kind of like a pipe or something. Yeah, that looks like a pipe now. Up to the top of the building. And okay, the length of the pipe is also going to be 12 because it's the same as the height of the building. So hopefully everyone is feeling this now, right? This is the length of the rope. This thing right here is the rope. This is the pipe. This is the building. You're up at the top and you're pulling in this rope, and as you're pulling in this rope, you're swinging that pipe up vertically. Okay, well, if this object were extremely heavy, perhaps you might want to perform some kind of calculations or whatever about the amount of forces that are acting on your rope and all kinds of other things. So it's very reasonable that we might want to know everything there is to know about this situation, the geometry of this situation, and the rates at which all these things are moving. Okay, so they do a lot of work for you in this problem, but already suggesting, hey, why don't you call this point x comma y? And hey, why don't you call this x? So okay, they've kind of, like I said, they made this problem a little bit easier. Okay, so let's do the problem. What does the problem say? Or what's our general method? Read and understand the problem. I think we've done that now. Pick variables for the quantities which are changing. Read and understand the problem, draw a picture, pick variables for the quantities which are changing. Well, they've sort of done that for us already, like I said, right? They are going to let S be the current length of the rope, and when S is 0, then you're sort of done with your job. And then X and Y are something. Well, what are X and Y? X and Y are the coordinates of the, with respect to a coordinate system in which the base of the building is the origin, X and Y are like the coordinates of the end point of the pipe or something like that. It's a little bit of a lame way of putting it. I think it's important so let's just kind of skip to the step where we add this to our picture. I'm going to drop a perpendicular here because this is ultimately a geometry problem. So if this point is x comma y, what that really means to me is that this is x and this is y. So what is x? You can describe x in words as the distance the top of your pipe is currently horizontally from the building, and y is the height from the ground of the end point of the pipe. I think that's pretty clear. That's sort of built into this diagram in which they suggested that you call this point x comma y. And okay, this whole thing was 12. And that makes this there for 12 minus y. 12 minus y. Okay, so read and understand the problem. Pick variables for the quantities which are changing. Here I sort of don't feel like writing out what x and y are, but x is like distance. I guess I will write it. Distance of top of pipe from building, where that is understood to mean horizontally. I guess that's all it could mean. And this is just the height from the ground, height of the top of the pipe from the ground. Okay, so I got my variables. I have 3 variables in this problem: x, y, and s. Read and understand the problem, draw a picture, pick variables for the quantities which are changing, add those variables to your picture. Now let's state the information given in the problem in terms of those variables. What am I being told? I'm being told that the winch pulls in the rope at a rate of negative 0.2 meters per second. In other words, this person up at the top is pulling in this rope at a constant rate. And if they're pulling in this rope at a constant rate, what's happening to s? Well, s is getting smaller. At what rate is s getting smaller? Well, translating this into the language of calculus, what I know is that ds dt is negative 1/5 meters per second. And what I want are 2 things. The vertical change, the rate of vertical change, and the rate of horizontal change at the end of the pipe. So I want to know dx dt, in other words, how fast is the distance between the end of the pipe and the building changing, and also I want dy dt. And like I said in the first part of this video, in order to solve this problem, we are going to have to compute general formulas for dx dt and dy dt, and to some extent that's the real related rates problem. But in order for this problem to have an answer which is a number, they're asking us to evaluate dx dt and dy dt at a particular moment. That's the moment when y is 6. So the true thing that we're being asked to do is to find dx dt when y is 6 and find dy dt when y is 6. Okay, but in order to do that, we need to get a formula for dx dt and dy dt in general. Alright, so we have been pretty successful now in sort of translating this word problem into kind of a geometry and a calculus problem. What's the next step? The next step is to find a relationship between the variables. Well, one of the things that makes this problem hard is that there are multiple relationships between these variables. One relationship between the variables is this Pythagorean relationship, and another relationship between the variables is this Pythagorean relationship. So I'm just going to write those both down here. X squared plus y squared equals 12 squared. That is simply a fact. And another fact is that 12 minus y squared plus x squared equals s squared. Now, what I do now requires a little bit of kind of creativity and initiative. So let me see. Read and understand the problem, draw a picture, pick variables for quantities which are changing, find the relationship between the variables. So here's the problem now. I guess I know what I want to do. I guess I want to get rid of one of these variables. So here's the thing. The idea here is that I know ds dt, and I want dx dt and dy dt. So I need to find a relationship between just s and one other variable. And so here, to me, I suppose the best thing to do is to kind of combine these 2 equations a little bit, right? Here I have that x squared is just 12 squared minus y squared. And so I think I'm going to take this expression and stick it in here. Why is that a good idea? That's just a good idea. Is that a good idea? I think it's a good idea. Sorry, 1 second. Oh man. Also I forgot to do this. Oh, it's going to be well, whatever. 1 second. Yeah, good. Okay, well, let's just do this a little bit faster. X squared is 12 squared. So what is this? What do we get here? We get 12 minus y quantity squared plus, that's 12 squared minus y squared equals s squared. Okay, and so by applying the Pythagorean theorem twice to each of these two right triangles, and I have ultimately kind of a system of equations here. I solve for x squared in one of them. This gives me what I want, which is the relationship between just y and s. All right, so what do I have here? I have 144 minus 2y. No, that's not right. I think this is the best way to do this problem. 144 minus, that would be 24y plus y squared. Is it so simple? Plus 144 minus y squared equals s squared. That's slightly surprising me, but okay. So, what is that? I think what I end up with is 288 minus 24y equals s squared. And so what I've accomplished now, I haven't done any calculus yet, but what I have accomplished is a formula which relates, I'm just double checking my work, which relates s and y. Now, finally, sprinkle some magic calculus pixie dust on this and take the derivative of both sides with respect to t. Well, the derivative of 288 is 0. The derivative of negative 24y will be negative 24 dy dt. And the derivative of s squared with respect to t is going to be the derivative of something squared is 2 something back inside for the derivative of the something. And I guess I can divide both sides by negative 24. And I get this formula, dy dt equals s times ds dt over, or negative s ds dt over 12. Okay, probably this is right. Let's see. This is the formula for ds dt, for dy dt in general, but of course ds dt is a constant for this problem. It's negative 1/5. And so if I sub that in, I get negative s times negative 1/5 over 12. So here the negatives cancel, and I get s over 60. Okay, so what this tells me is something relatively reasonable, I suppose. That dy dt is s over 60. Okay, so final answer, or at least half of it, what is dy dt? Dy dt, well, this is the general formula for dy dt, but if I specifically want dy dt at y equals 6, then I need to reach for this formula. Oh, wait, that's awkward. This formula tells me what dy dt is in terms of s. What is s? Well, now I have to do a sort of another geometry problem. This other geometry problem is, hey, what are x, y, and s when y is 6? So now I'm going to draw in this picture here in which, try to do this kind of carefully, when y is 6, then since the whole thing is 12, this is also 6, and this is 12. So I can do the Pythagorean theorem here, or I can just notice that this is a 30, 60, 90 triangle. So this will, in fact, be 6 root 3. And if this is 6 root 3, and this is 6, well then this is just also 12? Sure. Yep. And therefore, what have I just done? I've just determined that when y is 6, in fact, s will be 12. It kind of makes sense because we're exactly halfway up. Y is exactly halfway up, so it's completely symmetrical. This whole thing is, in fact, just an equilateral triangle sort of at that moment. And so the answer is 12 over 60. And so the answer is that the dy dt is, in fact, dy dt is in fact, or at y equals 6, maybe I should write, at y equals 6 is in fact 1/5 of a meter per second. I'll put a box around that. I would sort of like to check that really fast to make sure I'm not just being totally wrong here, but I bet that's right. Sorry for the dead time. Yeah. 1 second, 37 No, what is this? 29. 29 dy, yikes. Okay, that is the right answer. Good. Okay, so now all we have to do is, so this one is done. All we have to do is dx dt. Well, here, I think the smoothest way to do this now, believe it or not, is to just go back to this equation. This equation says that there's a certain relationship between x squared and y squared. So let's just differentiate both sides of this equation. If we do that, we get with respect to t. So this gives me 2x dx dt. Because of the chain rule. The derivative of something squared is 2y back inside for the derivative of y, so that's dy dt equals 0. So the 2's cancel, and what do I get? I get x dx dt equals negative y dy dt, and so what is the formula? The formula in general for dx dt is it's negative y dy dt over x. Okay, and now I get to ask. So this is the formula. Well, that's the formula. So finally, I get to ask. Okay, what is dx dt specifically when y is 6? And the answer is that dx dt when y is 6 is the opposite of whatever y is when y is 6, well, of course, that's 6, times whatever dy dt is when y is 6. That's what makes this kind of an advanced problem, right? dy dt is actually variable. dy dt is different at different times. But if I'm specifically asking for dx dt at the time when y is 6, then this formula is to be interpreted as I need to evaluate these three pieces at the particular moment when y is 6. Well, dy dt when y is 6 is exactly what I solved in the previous problem. So that dy dt is in fact 1/5. It's different things at different times, but now it's 1/5. And finally, what is x when y is 6? Well, I already calculated that is 6 root 3. And so therefore, the answer to this problem is negative 1 over, the 6's cancel, over 5 root 3 meters per second. So that is dx dt, and that is dy dt at this particular moment. Okay, back in a minute for the last one. Okay, last problem, number 31. An air traffic controller spots two planes at the same altitude converging on a point as they fly at right angles to each other. See figure. Okay, it turns out that we did almost this exact same problem already, so this is maybe a little bit of a letdown or something, but here was the general idea, that there's one plane here. How do I draw planes? Like that or whatever. And it's going in this direction. And there is another plane headed in this direction, and and they are this is this is don't touch the tripod. Then these two planes are traveling at the same altitude, so this view is from above. That's okay. And they are headed right towards each other. And they are converging on a point. If they're converging on a point, that means that they're headed for the same sort of spot.
That's an airplane!
Yeah, those are airplanes. That's right, my daughter's in the room right now. Okay. One plane is 150 miles from the point, moving at 450 miles per hour. Okay, I don't like the way they say this, because they're a little bit, I mean, it's fine the way they're saying this, I suppose, but what really is important is that there are these two planes. This is plane A, let's say, and this is plane B. And, well, plane A is moving at 450 miles per hour. That's simply a fact. 450 miles per hour. And
I'll be down soon.
Okay, good. The other plane is called plane B, is moving at 600 miles per hour. Okay, great. And actually, it's well, okay. La 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 la. So I think I understand this problem now, right? These planes are headed for a crash, And good. So what we want to know is at what rate is the distance between the planes decreasing, and how much time do we have to avert disaster? Okay, so read and understand the problem, draw a picture, pick variables for the quantities which are changing. Well, here it seems that the obvious thing to do is to let this be one variable and let this be another variable. In other words, let x be the distance, the first plane is plane A, the one moving at 450 miles per hour. X is the distance this plane is from the point at which their flight paths converge. And let y represent the distance plane B is from the point at which the plane's paths converge. And then the book even tells you that perhaps we should set the hypotenuse of this triangle to be s, where s is the distance between the planes. And so as these planes are flying, this distance is kind of shrinking, and we want to know how fast are the planes getting close to each other. Okay, all right, let's just do it, because I think there's really not that much going on. What do I know? Well, I know the speed of the planes, and so I know that dx dt, the change in x, is going to be 450. If you want to be technical about it, I guess you could write negative 450, because it is in fact true that x is decreasing, because x is getting smaller as a moves closer to that point. But I think it ends up kind of not mattering so much. And the other one I know is dy dt. What is dy dt? It's negative 600 miles per hour. Okay, and yeah. So what is it that I want? Well, I want, in part A, the rate at which the distance between the planes is changing. In other words, what I want is ds dt. And, okay, of course, it would be interesting to calculate ds dt in general, and we can do so, but this problem, in order to have a numeric answer, is specifically asking for dx dt at a moment in time. And that moment in time is the moment in which the first plane is 150 miles away, so when x is 150, and when y is 200. So at that moment, the question is, what is ds dt? Okay, so let's just go. Maybe this is not so hard, because the geometric now relationship between these variables is very straightforward. It's just a Pythagorean relationship, so we get x squared plus y squared equals s squared. And then we can... Amy okay? She's probably okay. She's 3. Then we can differentiate both sides with respect to t. So applying the chain rule 3 times, we get 2x dx dt plus 2y dy dt equals 2s ds dt. The 2's cancel, and I can therefore just solve for ds dt. What is ds? Oh, I'm getting busted right now. What is ds dt? By dividing everything by 2 and dividing through by s, I get this quite complicated formula. Sorry, the 2's gone. I get x dx dt plus y dy dt all over s. In other words, the formula in general for the rate at which the distance between the planes is changing depends on, quite reasonably I think, how far the first plane A is from the point of intersection, how far plane B is from the point of intersection, and the rates at which both of those planes are moving at, and how far apart the planes are. Of course, there is a relationship between x, y, and s. So let's just keep going. Okay, and then I can substitute these in, right? So if that's my formula in general for any planes in this formation, let's add in the information given in this problem, which is that dx dt is negative 450, so I get negative 450x minus 600y over s. So that's a formula for ds dt with the sort of speeds of these planes kind of inserted. And finally, we can solve for ds dt at the particular moment at which x is 150 and y is 200. And now, what am I going to do? Man, these numbers are so big. this is going to be, I have a negative on the outside, I suppose, and then this is 450 times 150 plus 600 times 200, but then all over, what is S at this moment? We can make a little side picture here, right? What's going on here? I have to just do the Pythagorean theorem. When x is 150 and y is 200, let's see, if I'm going to do this in my head, this might as well be 1520. This might as well just be 3, 4. So this is going to be 250. In other words, this is just a 3, 4, 5 triangle. So this is going to be 250 down here. Okay, and so being kind of smart about my simplifications, I guess I can take a 50 out of the top and the bottom. If I take a 50 out of all three of those, that's 3, that's 4, that's 5. And maybe then I can even take a 5 out of the 600 and the 450. That's like maybe a good idea. So that's like 120, and that is 9. And so hopefully the answer is, wait, that can't be right. 120 and 90, I guess. So if I did my arithmetic right, this is 270, 270 and 480, which is whatever that is, 60, 75, 750. So I think that the answer to this problem is 750 miles per hour, and that is exactly correct. Now, technically there's this negative in here, so the real answer to ds dt is negative 750, which makes sense because, of course, as the planes are flying closer and closer to each other, s is getting smaller, so the rate of change of s will be negative. I still think it's, well, there we go. Okay, so that was the calculus problem, and now comes the sort of cute little follow-up. Great! Now comes the cute little follow-up problem, which is how much time do we have until this happens? How do I do this? Oh, I know how to do this. This plane is traveling at 450 miles per hour, and it's 150 miles away, so it's going to take a third of an hour to get here. 1/3 of an hour, and I guess this one is 200 miles away, and it's moving at 600 miles per hour. So this really is, these planes really are going to crash into each other exactly if no one calls it off. And so the answer is that these two planes are 20 minutes away from crashing into each other. Okay, that's the end of that homework on related rates. Goodbye.